So goal of today's lecture is to understand the last two orchestration operation, namely monitoring and runtime reconfiguration. So inside the monitoring, we'll study about what is multi-resolution analysis, what is noise reduction, what is network topology, and messaging cluster monitoring. And around in the runtime reconfiguration, we will study what is load balancing and what is auto-scaling. And unfortunately, for all of those, there are different set of frameworks and algorithms you have to use. So this is why cloud computing gets really complicated, because before this we study about image selection, so we had different algorithm for that. Then we study about networking, there are different approaches for that, overlay, APIs, gateway, publish subscribe, Docker Swarm, bridge networking, so many different ways. Then we had a whole thing on benchmarking that decides your image selection and performance. And then after you are done with that and you deploy your images, then you have to care about monitoring and runtime reconfiguration. And they also need set of algorithms to do it correctly. And as I said, all of these steps are NP hard. If you think in traditional computational complexity, there is no optimal solution for doing each of them in a polynomial time, because each of them have many options to consider. That's why you need to have understanding. You either need to apply heuristics based on multi-criteria optimization. If not that, you may apply some machine learning techniques to optimize those things. So because they are NP hard, there is no direct solution. You can't search the whole space and find the correct configuration, find the correct solution for how much data to monitor, how much not to monitor. So you have to have some smarts in your system to do that. That's why machine learning and knowledge is so much important, because say with monitoring we'll collect a lot of information, but then how do you make sense of it? So applying statistics in machine learning to really find the actual metrics that is going to help you improve infrastructure is very important. So this is why we run cloud and machine learning together, so that you can link those two things and see how you can apply the machine learning knowledge to develop smart cloud monitoring algorithm or smart cloud runtime reconfiguration algorithms. They all are linked together. So should not study those two modules in isolation. They are connected. Those things are applied. Like in my group, we have written so many papers that use machine learning techniques to improve cloud computing. So you need to understand machine learning to be able to improve those operations. So as I said, the goal of today's lecture is to understand what do you mean by monitoring and what are the main complexity behind writing a monitoring algorithm and a monitoring software. Of course, when I refer to monitoring software, that means you're implementing your monitoring algorithm inside the software. Okay. Like for your coursework, you're not implementing any monitoring algorithm, you're just using CAdvisor, which is very okay for your coursework, but in the real cloud setting, when you deploy your application on public and private cloud in a hybrid setting, the CAdvisor is not going to work. You need to write your own monitoring algorithm. So we are going to understand what are the challenges with that. So going back to our old example, we have this multi-tier application where on the top we had load balancer, web server, app server, and the storage layer. When a user sends a request to that website, it goes to load balancer, it does some processing, then sends to the web server, then sends to the app server, then goes to Google Cloud Storage. And when this is deployed on public or private cloud, anything can go wrong with any of those components. And here I'm just showing one instance at each layer, but in reality there can be thousands of instances at each layer. For example, there can be 1,000 instances of web server, hundreds of instances of app server, and similarly many instances of the storage. And then if your application is slow in throughput or response time, you need certain mechanism to fix the problem. So this is some artificial data we have generated by monitoring across all the layers. So this data shows over the time scale what was the throughput. So in this, as per this graph, if you are a system administrator, you have to find which layer is slowing down your application. So what will you think based on this graph? Which layer is actually slowing down your application? Someone from that side? So here I am collecting through monitoring the throughput of each of the layers: storage layer, app layer, web layer, at different time. So based on this, your application is having slow throughput, and you have to figure out, debug, and say because of which layer this application is slow. So this shows the time, this shows throughput number of requests processed per second. So now, based on this data that you will get from the monitoring system, which layer you think is the slowest layer? Storage? Storage? So this is something you will do in your coursework as well. You will generate these kind of graphs. This is not based on real data, but this is what you get. So for throughput, is larger the better. So the smallest one is the storage one. So you have getting the least throughput because of the storage layer. Similarly, if we flip this argument other way, why my response time is slow? Because of the. So that was the throughput debugging. If I want to debug on the response time, so because of which layer my application is getting slow response time? Out of web, app, storage, app layer, or is it app layer? Right, so that's correct. It's because of app layer. So how are we finding this matrix? We are finding this matrix through monitoring, right? So now we'll understand what are the advantages of monitoring and what are the real challenges of monitoring, especially when you have deployed your application in the hybrid cloud or the public cloud. Because there are a lot of other things that impact your monitoring algorithm when you design it, and you have to take all those things into consideration when you design your monitoring algorithm. So I think in your coursework you will generate graphs similar to this, and you will analyze why something was slow, why something was fast, and you have to reflect upon your experiment results like that. I'm not sure if you get the similar one, but you have to somehow, from the data, have to reach some conclusion why you are reaching certain kind of behavior. For example, in this graph, we're saying my overall response time is high because my app layer is really slow. And why could it be slow? There could be many problems with the app layer. Maybe CPU saturation or memory saturation or network I/O saturation. There could be so many problems that is leading to high response time. And how do you how do you figure out? By monitoring as low resolution as possible. I mean, monitoring as finer parameters you can get on that application layer will help you find that problem, because the response time could be slow because CPU is saturated, so you need to know the CPU numbers. Or maybe memory saturated, or maybe network I/O is saturated, maybe disk I/O is saturated. So you need to have all those monitoring information to conclude anything around why something is slow or something is fast. So of course these response time and throughput, that concerns the applications. But if you are working for some data center provider like Amazon or Azure, along with the application, you need a monitoring that can monitor other things as well. For example, what is the temperature of my servers? What's the humidity? What's the airflow? Because all this will determine whether you're going to have a fire, or whether you need how you can use this matrix to optimize your air conditioning. So it depends on which layer in the cloud you're working on. If you're an application engineer, then you only care about application level metrics. But if you're a data center engineer, you need to monitor other metrics such as temperature of my rack servers, the total humidity, and how those temperature humidity affects my air conditioning power supply. Because ultimately they want to save on the power supply and power bill of the air conditioner. So based on what level of cloud you're working, either for the data center or the application, you got to monitor different parameters. That's why when you use Amazon, and I don't know if you know about their monitoring service called CloudWatch. Have anyone used CloudWatch? Amazon CloudWatch. So they only give you the basic metrics, right? CPU, memory, network I/O, disk I/O. They don't care about throughput and response time. They don't, because those metrics are very specific to certain applications. This is not specific across all data centers, so they don't want you to monitor those fine-grained application-specific parameters. They leave it to the developers or the application engineers to be able to monitor that. So you need to understand, okay, I can use something like CloudWatch for Amazon, but they only monitor very trivial abstract parameters, which may not be sufficient to debug your application. So you need to write your own monitoring algorithms to be able to debug those parameters. So you have to know what are the strength and weakness of the monitoring capability provided by the cloud data center provider, and whether that could be used to monitor my applications or not. So that is some kind of knowledge you need to have. So this picture shows what happens when you deploy application in a VM-based environment. This is not based on containers, so they are not microservices. They are those old monolithic applications. So if you really want to debug your application all the way from the application to the hardware, then you need to instrument the monitoring across each of those layers. For example, how fast is my network I/O, how fast is my disk utilization, memory utilization, CPU utilization, how fast is the communication between hypervisor and the virtual machine, how fast is communication between the OS in the VM and my web layer, DB layer, app layer. So you have to monitor all those things if you really want to drill down to the problem. Because if you don't monitor everything, your conclusion about the problem may not be very accurate. So then, of course, what's the challenge of monitoring everything across the stack? What is in the main challenge of being able to monitor right from the app to the VM to the hypervisor to the hardware? The instrumentation, right? How do I instrument across each of those layers? So mostly when you work on public cloud, they will not give you any control about how to monitor the hypervisor performance or the hardware performance, because it is given you as a black box. So it's a challenge for you. How do you monitor that? Possibly you cannot. So then you have to make your application monitoring as smart as possible so that you can drill down the problem from the access that you have on the infrastructure. So for example, by monitoring the app throughput or app response time, you should be able to drill down whether it's a CPU problem or it's a storage problem or it's a memory problem, network problem. So you need to have that knowledge. How do you relate the application level metrics to low level hardware metrics where you don't have the control, but you still need to be able to figure that out. So to define, performance monitoring method involves dynamically tracking the performance parameter related to your hardware, that is CPU, storage, network, and your software, that includes the virtual machines and the application components running inside the virtual machine, that will be web server, app server, and the DB server. And the key is, as much information you collect, it will be easier for you to find the problem in your application. It will be much easier for you to debug the problem. Right? So if you want to relate that to, like, when you write a code in, say, Eclipse environment, you use F8 key to debug your code, right? And everything is there. You can debug your bugs in the code, and that everything is there on your computer. But if you want to debug this cloud application, that's not going to happen because it's a distributed deployment, and you cannot just debug this kind of application based on your programming environment, because programming environment is just a static environment where the code is actually not deployed in real setting. So this will only happen when you have to collect all the monitoring data to one place, and then on that, so you have to do a lot of data analysis to be able to find the problem. So here problem is not debugging your code, but actually debugging the instrumented monitoring data that you collect from your monitoring system. And actually for companies like Twitter and Facebook, managing monitoring data itself is a big data problem for them. So those people who are doing data science, being able to process and analyze and find faults for monitoring information is a big data problem, and they apply many stream processing techniques and machine learning techniques to be able to debug that problem. Just imagine that you have a server infrastructure with thousands of software components running on different virtual machine, and each of them is sending you data every 1.5 seconds. That is done by, say, Docker. And then all those data, you are getting 1,000 data points every 1.5 seconds. And in just 1 hour, just imagine how much data you're going to get. And then from that data, you got to figure out where is the problem. So that's why you need smart techniques to be able to figure out those problems. So one of the way to figure out that problem is to use stream processing. So if you take the big data module in the next semester, they will teach you Apache Spark or Apache Storm, where this monitoring data directly feed into the stream processing system, and stream processing operators can find these faults based on the rules you define on the real-time data. So you don't have to take these thousands of data points after every hour and debug it. You can debug it in real time. So there are many ways to do it. But for what we need to understand is debugging and monitoring and finding faults for monitoring data is a big data problem, and we need solutions that can solve that, which can be based on one of the big data programming model that could be MapReduce or could be stream processing, one of those. If you want to do based on historical setting, then you can use MapReduce, that we will cover in tomorrow's lecture. If you want to do in the real time, then use stream processing to do that. Stream processing coupled with machine learning and other techniques. So now it's coming back to what are the main advantages of doing monitoring. So before we go into that, you see the complexity of monitoring increases as we add more and more data center. For example, if you are purely private or purely public, monitoring is a bit easier. But if you add multiple data center that has both public and private, it becomes hybrid cloud, and the monitoring becomes more and more difficult because of the issues we talked about in the virtualization lecture. Each of those can use different kind of hypervisors and container, and how do you collect data from there will differ. Similarly, monitoring across the infrastructure, platform, and software service layer on its own is a bit easy, but if you do it across all the layers, it gets more and more complicated, and the level of instrumentation needed has become more and more difficult. However, having said that, we still need to monitor. If you are not able to monitor your application, then you cannot run your application on public or hybrid cloud, even private cloud, because you just wouldn't know whether your application is delivering the feature it's supposed to deliver. And then if you are a commercial company and say for example Facebook, right, if they're not monitoring the performance and people are going to their application and they're getting no response, you will just stop using Facebook, perhaps go to some other application that gives you better performance. So making sure that your application is delivering the performance to the users on the level that is going to satisfy the user is very important to keep your business going. So these are the key to why you think people use Google search, because Google search is the fastest, almost one of the fastest search engine ever. Before Google search came into picture, people used to use Yahoo and MSN and others, right? Because people switch to Google search because they are just more responsive. And how they do it? Because they are very sophisticated monitoring and resource management techniques implemented in the data center that they can process your search requests much faster than Yahoo and other competitors. Same goes for Facebook and Twitter. They're very responsive services, but they all do so because their data center engineers are really, really agile, and they implemented these sophisticated algorithms to be able to monitor, find problems, and scale problems on as it appears. So monitoring is required for doing many very important activities in case of public or hybrid cloud. First of all is the capacity planning. So capacity planning means, say if you are a company, you want to deploy your application on say a public cloud. So, and since say you are a company, you don't know how many users are going to use your application, so you just start with 1 VM or 5 VM. And as users come and user services, you keep monitoring your CPU, memory, throughput, response time. And once you observe that through monitoring that your throughput and response time is getting really slower, you scale it up. So that monitoring will help you grow your infrastructure. So it will help in capacity planning. So if you didn't have that monitoring, you wouldn't know whether some users are facing delays, some requests are processed at a slower rate. So those kind of things can only come from by monitoring those user requests. So accurate monitoring will help you to do a proper capacity planning. Without that, you cannot. Because not all application workload can be modeled using the Poisson distribution and the normal distribution during the course, so they are not representative of real workload. So the only way to find your real workload trend for application is through monitoring, and then use the information to plan how many servers I will need based on as users are using your services. So you can derive that from your monitoring log. I'm not sure if you have looked carefully into the service level agreement provided by Amazon. So whenever you sign up for Amazon services, they give you this 99.99% availability, that whenever you buy a VM storage, it will be available for 99.99%. But if you are an online gaming company, is that a sufficient SLA for you, that your VM is just available? It's not, right? The SLA that you want is the throughput and response time. That when user comes to application, they get a response as fast as possible, and your server is processing as many requests as possible per unit of time. And moreover, so going back to our Amazon example, say Amazon promises that they will deliver 99.9% availability. How do we make sure that they're delivering that? The only way to make sure that is to monitor. Otherwise, we wouldn't know. Then how do you think Amazon is billing you? Amazon again billing you based on monitoring, because as I said, these public cloud providers, they bill you on per hour of time, or how much storage you use, how much network you use. So again, those kind of things, Amazon has the information by monitoring you, all the requests, all the processing, everything you do. So monitoring is just not for performance management, but it's required for capacity planning, to monitor the service level agreement, and to do the billing. So that is for, then of course the troubleshooting and debugging that we discussed till now. So if something goes wrong with your application, you need the monitoring data to be able to find the problem, which hardware or which software has the problem. Similarly, Amazon needs the data to debug the problem in the data centers. So troubleshooting both at the level of application as well as the data center both needs the monitoring information. And based on those troubleshooting, you do your performance management. For example, you do your auto scaling to improve your response time, to improve your throughput, to reduce CPU saturation, memory saturation. And of course, monitoring also help you in security management. For example, you can use monitoring of your network traffic to determine intrusion detection. If some outside hackers are trying to attack your network, that you can only do by monitoring the traffic at the network level as well as your application level, and from there use some sort of machine learning algorithm like Bayesian networks to detect whether some security breach has happened. You can also do monitoring to detect whether the user who has logged into the virtual machine or the application has the credentials to log in. For example, if you use Amazon, they have credentials based on secret key and the access key to logging onto the API. Similarly, if you log onto the virtual machine, you use the PKI key pair. So they can monitor whether the user who is using the public-private key pair is the user who actually authenticated to the system. So all these things can only be possible by having monitoring for each of these different aspects. So you see, monitoring is one of the fundamental pillars of cloud application engineering, and it is required for so many things. So normally if you go to Amazon, they will have a team of more than 1,000 people working on monitoring infrastructure, and they are working across different verticals like billing, capacity planning, SLAs, troubleshooting, based on which group they are part of. So it's a very big, massive thing for cloud computing, being able to do really efficient and optimized monitoring, right all the way from the application to the hardware to the network to everything. They need to monitor everything to make sure that everything is running the way it's supposed to run. Of course, till now we discussed that monitoring is good because it has so many advantages, but then again there are challenges with monitoring. The first one is scale and complexity. Why do you think it's complicated? So the first challenge is actually monitoring to the level which will help us debug the application really complex. So just try to think from your perspective of your coursework, for example, right? So instead of monitoring everything using CAdvance on your machine, just throw those microservices on thousands of cloud server, and now you have to monitor. So, right? So it becomes really complex, right? The first thing is, how do I collect information from all my microservices, right? So first thing is we have to write certain agents which can run inside the microservice or inside the Docker engine that can give me information about CPU, memory, network, response time, throughput for each of those 1,000 microservices. And then how do I collect that data? Where do I collect the data? Do I put the data inside the same data center, or if it's hybrid data center, do I collect the data in a private data center? So this scale and complexity will be really for you to consider. So for example, if you're running application on public cloud, right, and if you if you have a very sensitive application, you don't want your competitor to know your application logic. So you don't want to store your monitoring data on public cloud. Just to give an example, when you're using CloudWatch to monitor application, CloudWatch is storing your monitoring data on the cloud storage provided by Amazon, the Amazon S3. So Amazon can go to your Amazon S3 account if they want, and they can understand how your application is performing, from which part of the world your application are popular, for example, and they can know your business secret, and they can offer a similar application to beat your business, for example, right? So this leads to leakage of monitoring data, and from that leakage, your competitor can gain the extra knowledge to create a competitive application. So it may not be in your interest to use CloudWatch for monitoring. You want to use your own monitoring infrastructure, your own monitoring algorithm. So then the challenge is for you that you have to write your own monitoring algorithm. Then you don't want to store that monitoring data on the public cloud storage. You want to bring that monitoring data to your own storage inside the private cloud. But then it leads to cost of monitoring, in the sense that for every byte you transfer out of Amazon or Azure data center, they charge you some money. On per transaction, they charge you few US dollar pence, and then if you are having millions of messages every day, it can cost a lot of money. So you have to analyze how much monitoring I want to do and how often I want to get my data out of data center. So cost of monitoring is one of the critical factors. This cost is different from cost of the virtual machine or cost of the container that we study in lecture 2 in cloud economics. So cost of monitoring is also something if you have to factor in your economic model when you write your monitoring algorithm. And then, as I said, when you have thousands of microservices running, you have to somehow inter-network those microservices together. So what kind of networking architecture you will use to interconnect those monitoring agents? Any idea? So we need certain way to say inter-network thousands of monitoring agents running across thousands of servers. So, of course, the most trivial is centralized, but it just is not scalable. So you have to use some more efficient way to inter-network a monitoring agent. So any idea what kind of technique you can use? So networking or monitoring agent becomes really a big issue in large-scale infrastructure. So there are many techniques available. You can use based on hierarchy. You can use trees, multi-level trees, where you have multi-level super manager and sub managers to connect different levels of infrastructure. If you want to do a more efficient one, you can use something called peer-to-peer networks, where each of those monitoring agents are connected based on a peer-to-peer topology in which there's no centralized elements, and based on what kind of peer-to-peer topology you use, you get different message complexity. For example, we had one of the paper in which we used something called distributed hash table. So what happens in distributed hash table, if you use distributed hash table peer-to-peer topology, you can debug your problem in log n steps, where n is number of microservices. So for example, if you have 8 microservices, you can debug the problem in 3 steps, in 3 iterations. So it's 2 raised to 3 is 8. So log of 8 is 3. So you have to use some networking methodology that is scalable, and if you can get a methodology which is logarithmic to number of nodes, it's the most scalable one. So that's one example. So you have to take care about that you collect enough monitoring information from enough number of servers without creating a centralized system. So you want to have to create a decentralized system, so you can use some peer-to-peer topology, and then you have to collect sufficient data that will help you monitor those information. And there are different ways to network those agents. We can be based on self-balanced trees, based on peer-to-peer topologies, based on B+ trees, based on different graph structure. So all this B+ tree and peer-to-peer distributed hash table, they are some kind of distributed graph structure. You can network your monitoring agent. So that's a challenge, and you have to, when you write a monitoring algorithm, you have to figure out which kind of graph structure you want to use to connect your monitoring agents. Okay. If someone is really interested in that, I can send some papers that are written by our group and others. You can understand what kind of graph structures are available to you to develop your monitoring systems. So those kind of graph structure normally taught in data structures course when you take computer science courses, they teach you in data structures. B plus tree, K tree, this distributed hash table trees, quad tree, there are many trees available to create those kind of data structures. And as I said, we want to collect as much data as possible about our infrastructure, but then you have to think the trade-off between instrumentation and intrusiveness, because you don't want your monitoring agent to be too intrusive to your application. For example, if I have a microservice that is doing certain kind of computation, but if 50% of time I am wasting in monitoring the microservice, then it's not a good approach. So you have to come up with a strategy to monitor in that such a way that you collect sufficient amount of data without actually affecting the performance of underlying application component. Similarly, for example, on the cloud hardware, I'm monitoring the CPU utilization. So I have to instrument the hardware in such a way that I'm not consuming a lot of CPU in actually monitoring the CPU. So I have to instrument in such a way that it's not very intrusive. So that is something you have to keep in mind as well. So as I was talking about Amazon monitoring, so if you use Amazon CloudWatch, it monitors your CPU, disk, networking features, but it doesn't care about your process configuration, application latency, error rate, throughput. So if you want to monitor these, what can we do? So if you're using Amazon, it only monitors the hardware features, CPU, disk, and networking on that host. And I want to monitor some application-specific feature. What can we do? We have to write our own monitoring algorithm or use some. There are a lot of cloud startups that offer those frameworks for licensing as well. So you can use one of those to monitor these things. Normally what people do is they use one of those open source framework and then modify the code to suit what they want to monitor. So that's the approach. So these cloud providers will always give you the basic parameters, which is generic across all the applications that run on the data center. They never go in detail of the actual application level parameters such as latency, throughput, error rate, process memory utilization, process CPU utilization. They never go in that detail. So this is one example of one application that runs in London Stock Exchange. So one of my friends works there. They have this stock application, and they have 469 software components, more than 2,000 communication links, and more than 40,000 different dependency patterns between those software. And this is a real-time trade application. So what happens in stock exchange is they have to update the stock price in real time. So this infrastructure has to keep running all the time and give the real-time response. So his goal is to keep this running by being able to find those problems across those 470 software and this 2,000 communication links. So see how hard is this problem to be able to debug and monitor at the level of enterprise application like London Stock Exchange. So like London Stock Exchange is almost the second biggest stock exchange after New York Stock Exchange in the world, and they cannot get this wrong. So the guys running it really need to know what he's doing. Of course, he has a team of 500 engineers helping him doing that, but these are the type of, if you work for big companies, these are the type of application you have to deal with, and you have to apply your knowledge that you learned in this module and machine learning module to be able to monitor and debug and find problems. Because if you are not able to update your stock prices in real time and something fails, then all the brokers will go away from your stock exchange and the business will go down. So this is really like a mission critical application, and then everything has to be done in real time and nothing can go wrong. So this is the level of complexity that you will face in real enterprise level applications. Of course, so as I said, monitoring in single cloud is difficult, but is less difficult than monitoring across multiple clouds. For example, if you have some microservices running on your laptop, some running on Amazon, some running on Azure, and then you want to write a monitoring engine or algorithm that collects information from the three different infrastructure and put it in one place, that is more complicated than being able to monitor each of cloud on its own. So like even you find hard to monitor just on a laptop using C-Advisor, right? Then, but if you go and distribute your microservices across different clouds, how do you do that? So that's really challenging. To solve that problem, we developed a monitoring system ourselves that we will demonstrate to you around 6 p.m. today how we did that. So we can monitor across Amazon and Azure, so we'll show you a demo of that. But of course, it took him like a PhD student almost 2 years to develop that solution and get it working in a way. And the approach was based on inside each container engine and inside each VM, we deploy an agent. That agents collect information about that VM or container. And then those agents are inter-network based on self-balanced B tree to a manager. And they send information to the manager, and you can connect to the manager and you debug your application. This was our approach to monitoring the application that was deployed across Amazon and Azure. And we showed that through experiment that our monitoring algorithm is better than what is given by Amazon CloudWatch or Microsoft Fabric Controller, the monitoring tool which is provided by those companies. So of course, so you can write a software agent that runs in container, runs in VM and collect all the data. But then there's also challenges with that. At what resolution you are monitoring? Just to see this example, you have the app layer, that's a trade application in the app layer. Then you have the DB layer, and you got to monitor. So for example, you are monitoring your DB layer every second, CPU and disk, and you are monitoring app layer per minute, right? And suddenly you found out that your end-to-end response time is not very good, it's slow. But you can't actually use this data because your level of monitoring is very different, because here you are getting data every second, they are getting data every minute. So you can't correlate the data for every transaction because the resolution, the monitoring resolution is very different. So although you have instrumented, and so you're getting CPU disk every second, you are getting SQL and everything every 10 minutes, and you're getting the other transaction 1 minute. So you see, each of those layers, you have resolution of 1 minute, 10 minutes, and 1 second. So even if I collect all this data, my resolutions are very different. I can't use the data to debug my problem. I cannot find out why throughput was less or more, why response time was less or more. So to be able to use this data, you have to monitor at the same resolution, either every second or every minute or every 1.5 seconds as per Docker. Then only you can use those data. So monitoring is just not about you write a software agent that collects data on certain time period, but all those agents and monitoring across each layer should be synchronized and should be at the same resolution for you to be able to make sense of the problem. Otherwise, even if you collect a lot of data points, it's not going to really help you find the problem. So even imagine that, okay, we now monitor everything every second on each of those layers, and then still we have to follow a certain technique to actually find the problem as depicted by this picture. For example, on the application you're getting high application response time, and now you have problem. You have monitoring information from the web layer, app layer, and DB layer. So you have to figure out whether my high application response time is because my Tomcat server is slow, or whether my app logic algorithm has some bug, or the SQL query execution on the database is slow. And why could that be slow? Because maybe my database schema is not correct, because I'm not caching the query result correctly in the DB. So you have to, so what message here is, based on your application architecture, you have to find different data flow across each of those layers and how they are dependent. For example, a request from web layer goes to the app layer, goes to DB layer. So that as the web layer, you are just doing simple transformation like serving static HTML pages. Okay. At the app layer, what you're doing certain computation by fetching data from the database. So you have to know this different data and control flow in the application, and then based on that, you have to build your debug graph, and then across those graphs, which will look like something like this, you have to find out where the problem is. Of course, for a 3 component, you can make graph in using static methods by yourself. But if you have like those stock application with 1,000 components, you have to generate this debug graph automatically. You can use Bayesian trees or some other machine learning algorithm to make this debug graph automatically and see how each of those layers are dependent and then where is the problem. So being able to make those debug graph or the fault graph automatically is key to pinpoint the problem. So one of the techniques they use for that is called multi-resolution analysis. So what they do is they first look at each layer at very high resolution, look at, okay, which layer has highest CPU utilization. Maybe they see that maybe first CPU is saturated. Then they look into network, then disk IO. So you have to go this debugging step by step and then reduce the resolution one by one. For example, we find the point that, okay, the CPU at web and app are okay, but at database layer CPU is very high. Then we go more into CPU and say, okay, is that CPU actually affecting the SQL query processing? Is that CPU affecting my cache to RAM synchronization management? And then from there you can find the problem. So you have to start debugging at the very high level and then go slowly to the lower level to localize the problem. And based on what problem you will end up with different debug graph or the fault graph based on what problem you have, response time, throughput, or CPU saturation. In fact, in the databases, you can be as the CPU or the slow application response time could be as simple as some of your table is not normalized. You have a lot of tuples inside. So whenever you do a join query, it makes your application slower. So to be able to do this multi-resolution analysis, you have to know how each layer is dependent on each other, first thing, and then inside that layer, what could go wrong. You have to know what could go wrong. The monitoring system will just give you the data, but it will not tell you at DB layer what will be going wrong, at app layer what will be going wrong. For example, the web layer could be slow because it is trying to fetch a HTML page from a storage service. That network is slow. So that because of that, the response time is slow. The DB layer could be slow because one of your table is not normalized with other table on which you're doing the join queries. So of course, monitoring can give you all the information, but you are, as a cloud application engineer, you have to know at each layer what could be going wrong and how it is dependent on each other. So that's something you need to figure out based on your intelligence. That's something monitoring cannot do, and then use that intelligence to do this multi-resolution analysis. So following on that, so you first have to do is you have to determine the dependency between each of the layers, avoid those monitoring alerts which are not important, and then try to find the real threats. So again, how we apply this to specific application is based on your application itself. There is no generic methodology, but you use this multi-resolution technique and noise reduction based on what software and hardware components are part of your system, what monitoring alerts you're collecting, and how they are correlated. So that's something you have to build based on your intelligence, the debug graph. And the debug graph for each application is different. It's not the same. For example, a debug graph for a gaming application is different from a simple web application or content delivery application or scientific workflow. Each of them has a different debug graph. So what are the ways to determine the dependency between the layers and finding out that which events are important for me? Benchmarking. You figure out that through benchmarking, and then you feed that benchmarking knowledge to your monitoring system, and based on that you make your debug graph. Because benchmarking will tell you when components work together, under which scenario, when they don't work together, what goes wrong. So you have to benchmark under different scenarios to find out those inter-component dependencies and see which monitoring events are important for you and which monitoring events are not important for you. So that's where you have to go back to the benchmarking methodology, and from there you can determine, okay, what's the actual dependency between each of those layers, and then debug just based on those parameters. Other tools that you can use to debug, use some kind of correlation matrix. For example, you can monitor the CPU and network and throughput across each of the layer, and then see how correlated they are. If they're correlated by more than 90%, then that is one of your dependency. For example, high response time for application is correlated with high CPU at DB layer and high network I/O at the app layer. This kind of information they can get from correlation matrix, and you can use different statistics techniques such as regression models to know your correlation, and from there you can determine your correlation between different metrics and different layers of the system. And then from that correlation you can use many machine learning techniques such as auto-regressive integrated moving average or mixture density network. There are many, so this is one of the deep learning techniques. There are many techniques available for you to debug application. So are you learning these in your machine learning course, any of these methods? No? Maybe Bayesian? So you can apply Bayesian as well to actually able to predict what can go wrong with the data. So just to summarize, the key here is to be able to collect information at all the layers, then to be able to find out which information are important for me, then to find out which events are correlated with each other using correlation and regression model, and then from there you build your own debug graph using one of the machine learning techniques such as MDN or ARIMA model, and then from there you implement that as part of your monitoring system so that it can detect those faults automatically at runtime. Very, very hard problem to solve, but this is what the engineers in Amazon Azure are doing. They do all those things and they come up with these monitoring techniques that can ensure that their data center is available 99.9% of the time. So why they can do it? Because they do all these things very correctly and in an optimized way.